Hi everyone, Professor Christina Silver here from Cal State Long Beach speaking, and in this video we are going to talk about a balls in a bag experiment. Now I know this paragraph in front of us can seem a little bit overwhelming. Let's go through it together to see if we can't make it make more sense. Now this is an activity from our textbook, so it might feel a little bit odd, but let's go through it regardless. One member of your group will, without the others seeing, place 5 balls of 2 colors or use other objects of 2 colors that cannot be distinguished by feel into an opaque bag. Only that person knows what colors are in the bag. Others in the group draw a series of 5 balls, replacing each ball after drawing it and noting its color. The others then collectively make one prediction as to the number of each color of balls that are in the bag. The prediction is an experimental probability. How accurate is your prediction? In that first paragraph here, what they're talking about is developing an experiment, and the whole point of not being able to distinguish the feel of the objects is so that the probability is equal for each ball or object in the bag. If they're the same shape, weight, and feel, um, you're not more likely than the other to grab one in theory. Um, so in the next paragraph, consider the sample space for drawing 1 ball from a bag containing 2 red balls and 3 blue, replacing the ball and then drawing again. This sample space consists of all possible outcomes and is made much easier by thinking of the balls as numbered R1, R2, B1, B2, and B3. Counting the possible outcomes requires that we list all possible pairings. If one draws a blue ball on the first draw, replaces it, and then draws the same blue ball, that outcome is considered different from one where after replacing, a different blue ball is drawn. Listing all outcomes should be done in a systematic, organized way to ensure that all pairs are included and none are counted twice. And they have all total possible outcomes here. I'll put parentheses around it and use proper notation as saying this is the sample space. So we want to get our experiment taken into consideration first. You're going to draw 1 ball from the back, replace it, and then draw again. So if we want to write out our experiment a little bit more precisely, draw 2 balls with replacement. That would be the shorthand to say that. Now, I personally do much better with a picture, and I'm going to draw a fabulous bag. There you go, there's my bag. And then we have 2 red, 1, 2, and they're numbered. And then 3 blue, 1, 2, 3. Now, this bag, very precise. Everything has a color and a number, but you can't feel any different. They all look very similar. And you shake up this bag and you pull one out. And so you might get on your first attempt, you get the first red ball out. And so what could happen on your first attempt is anything where you get the red one first. And oh, it's systematically written in the first column. And then we put that ball back. Shake up the bag. Here, let's mimic that happening. Shake up the bag. And this bag is very stagnant, so they didn't move around too much at all. And you put your hand back in there, and oh, we got red ball 1 again. So we're going to go record what we got, and in fact, it's the first outcome. The probability, let's put that ball back in the bag. The probability of getting red 1 followed by red 1 is all of the ways we can get R1, R1. We found it. It's the first one out of all of our possible outcomes. Well, this first column has 1, 2, 3, 4, 5 options. And there's one, two, three, four, five columns. So that's going to be 25 total possible outcomes. So the probability of getting R1 is 1 out of 25, or 1/25th, however you want to word it. But what if instead I wanted to get the probability of R1, R2? Well, let's erase these highlights from before. We want to find the probability of getting R1 followed by R2. I see R1 and R2 together here, but I also see R1 and R together here in the second column, and there's a distinction. Because we've labeled everything so precisely, and I'm picking up a ball, looking at it, recording it, and putting back down into the bag what I got, I can only get in order R1, R1. So even though the second highlight uh, has R1, R2, it doesn't count in our list. So we're not going to highlight that one. We can get R1, R2 in that order, 1 out of 25 ways. What if I just wanted to get the probability of 2 reds? Well, I hope it's obvious since that we have everything so precisely written. We have the color for each ball, and each ball has its own distinct number. The probability of getting each ball individually is all the same because they're the same size, shape, and weight, but we know how to distinguish between the different colors. And so if I wanted to get 2 reds, I would just go through and say, okay, here's one with 2 reds. Here's R1, R2 is 2 reds. That's all in that column. I can do R2 and R1 with 2 reds. I can do R2 and R2 as 2 reds. The rest are blues and reds, and the last columns are also all blues and reds. So I would get 4 ways to get 2 reds out of 25 possible ways. And that's really awesome about labeling everything precisely and having your sample space as every item is equally likely. But an issue comes up with a tree diagram. Let's try to draw the tree diagram. So the tree diagram for this specific example, where we have red balls and blue balls and they're all labeled perfectly. Well, the first we'll do branches, and that's why it's called a tree diagram. And you can draw it sprouting out like top to bottom or left to right, whatever you prefer. I, for space, will oftentimes write it down the page rather than across. It's your choice. I drew 5 different branches because I could have red 1, I could have red 2, I could have blue 1, I could have blue 2, or I could have blue 3. All of those are equally likely for those reasons you mentioned before. These 5 branches represent the first uh, draw and replace. Now, for each of these scenarios, well, red ball 1, I replace everything, so I still have 5 options here. I could get the first red ball again, or the second red ball, or I could get the first blue, or the second blue, or the third blue ball. And this scenario could happen here for the getting the second blue ball first. Or I can get, or the second red ball, sorry, and then I can get the first blue ball. And notice I'm trying to really cramp stuff in here to try to make it fit because there's just not enough space when you have everything drawn out individually. Everything gets really crowded. But the benefit is I know each one of those branches is equally likely to occur. So if I'm trying to find, like we were a moment ago, 2 reds, I just go through and find the branches where I end up with red, 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 count up what I've highlighted. I got four before, and then I know there's 25 total possible outcomes because there's one, two, three, four, five on that branch, six, seven, eight, nine, 10 total so far. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Gets a little bit hectic when there's so much, but again, because everything was labeled properly and everything was distinguishable in two different ways, we had the color distinguishable and a number for each of those different colors that are the same. Everything's equal, it's all great. That's not the only way we can draw a tree diagram, and honestly, it's not my preferred way either. This is because I really like to be able to visualize clearly what's going on each time and keep note of the probability each time. So here is a condensed tree diagram. I know someone's going to ask me, well, which one do we have to do? I don't care which tree diagram you use. It's a tool to help you learn and grow and make more sense of the problem. So whichever one makes more sense to you. The first thing I'm going to do is draw out my sample space. I could get red followed by on the first pull. So let's test it out. Hold on, give me a second. Let's start again. We have a condensed tree diagram. We could get a red ball or we could get a blue ball. On the first pull, probability of red is equal to, well, there's 2 out of 5 of them. And for probability of blue, it is 3 out of 5 of the balls. So that's the probability of red and blue when I first start with replacement. Because I'm doing with replacement, that's still the probability each time. So what I'm going to do is draw my tree diagram. My options feels a little bit fewer now. I could get red first, or I could get blue first. And for our red option, let's make this a little more interesting like before. We could get a red ball or a red ball. And for blue, on the first pull, we have 3 blue balls. So you can write R and B, or you could draw a picture, whatever's easier for you. It doesn't bother me at all. Now, because the probability of each of those branches is not the same, I'm going to write it on the branch. For blue, I have a 3/5 chance of getting a blue ball. And for red, I have a 2/5 chance. So I'm going to write those to notate them. And when you do a condensed tree diagram, you must write your probabilities for every part of the tree diagram on all of the branches. Well, now from there, if I get a red ball first, again, the first part is the first draw and replace. And replacement is only happening because it says we're doing with replacement. And so when I get a red ball first, well, I can get a red ball or a blue ball. And let's draw those pictures again. We can get a red ball or a red one. Probability is 2/5 because it's with replacement. Or we could get 3 blues, one of each. We're only going to grab one, but we have 3 of the blue balls in the bag. And the probability is 3/5 because it's with replacement. Now, over here, if I got a blue ball first, I have the same setup, but I actually have to shrink this. I have to shrink it because I draw really big, but it's much less large and confusing as it was before. The only reason why my tree diagram is not taking forever to draw because I have a tablet, I'm able to cut and paste stuff to happen on here. Um, this tree diagram before that's not condensed take a while. But then the calculation was real fast, we just find it. Let's see the difference here if we're trying to find the probability of 2 red. Well, what I want to have happen is the probability of red followed by red. And because these two events are independent, they don't depend on one another, they don't affect one another, I can break this down as the probability of red and then means to multiplier followed by getting red again. Well, the probability of red the first time, the first draw is 2/5, and we're getting that from right here on the tree diagram, followed by, and then getting red a second time is the other branch, and it's also 2/5. Well, 2/5 times 2/5 is 4/25. And oh, that's exactly what it was before. Well, I think it's about the same work, but easy in other ways. I really prefer condensed tree diagrams because I can see all the pieces going on, can keep it tight and compact, and I can still get the idea of what's going on. Something someone might ask is, well, how the heck is it 25 on the denominator? We only had 5 different balls. How did it go from, 5 possible outcomes of 1 or 2 red ball and then 1, 2, or 3 blue ball? How did it get to 25? Well, using the fundamental counting principle, I like to think about it this way. The first line we got going on here is the first number of choices or number of outcomes. We had 2 red balls and 3 blue balls, so that's 5 options. And because we're doing with replacement, our second number of choices is also 5. That's equal to 25, and that's the size of our sample space. This is using the fundamental counting principle. Um, let's go a little bit further here. This might be a long video. I'll put time signatures. I apologize. I just really love this stuff. What if we did it without replacements? Let's take a look at that. And I'm only going to look at it with the condensed tree diagram. What if we did a drawing, 2 balls without replacement? Still the same scenario. Here's our fabulous bag. We have 2 red balls in there and 3 blue. They're all still the same size, shape, and weight, so we can't distinguish that way. It's just their color. Um, but without replacement, we still have 2 options for the first part. We could get 2 reds first, or we could get one of the 3 blues. But now there's a subtlety coming in. I'm going to use a different color here in hopes of uh, keeping this a little bit in our minds. This is the first drawing, no replacement. All right, let's just say that we got a red ball first. Let's say it's this one. Well, now that ball is gone. It's already occurred. If I'm doing my second drawing, which is drawing more branches down here, I still could get red or blue, so I can draw red balls. We had 2 before, let's just draw them anyways. Or I can get one of the 3 blue. But wait, I took out a red ball and I'm holding it in my hand now. I'm like a little kid. I'm not giving it back. It's in my hand. You can't have it back. So I don't have two red balls anymore. This one is gone. I'm gonna erase it. It's no longer an option. If I got red first, I'm holding it in my hand. I can't get it again. So I've just reduced the number of elements or parts that are in my bag on that second drawing for red. And so before, my probability for red was 2 out of 5. Now, in my picture here on my tree diagram, I only have one red ball. And out of, in fact, a total of 4, one of them is red, 3 of them are blue. The probability of getting blue in the second drawing, if I got red first, is 3/4, because that 4 comes from the one red. Let's highlight that. This 4 comes from the one red option and the 3 blue options, because I've reduced my number of elements that I can choose from. Like again, before that 5 comes from the 2 reds that I started with and the 3 blues. Some subtleties going on here. So if you have questions, please reach out. Let's get rid of that subtraction of that ball. Let's look if we got a blue first. Well, probability on the first drawing of getting blue is 3/5. Then let's start like we did the last time. Let's just draw our 2 branches. Without even thinking, I'm going to draw my 2 reds that I started with before to make those a little bit nicer circles. And then let's draw my 3 blues. And let's say I picked up this one here. Well, I'm holding that blue ball in my hand. What happened is I got blue first and I'm holding it. This is mine. You can't have it. I'm going to hold it. You can't have it. Well, then I have to get rid of one of my blue balls from the bag. I only have 4 balls in the bag now. So I'm going to put a 4 over here and a 4 over here and look at my options. I still have the 2 out of 4 options here for red, and in this case, 2 out of 4 for blue as well. But we got to be careful of those subtleties there. If you're doing drawing without replacement, you always want to make sure you think about what is still available to choose from. Now, if I want to try to find the probability of 2 reds without replacement, in words it looks different. But when I do some shorthand, probability of red followed by red, it looks a little different. I'm going to go ahead and highlight the part that I care about. Probability of red, red. Well, red first, red second. I'm going to get the probability of red in the first case. And then probability of red in the second case. Red in the first case is 2/5. Red in the second case is 1/4, because I'm holding that first red ball in my hand. I'm saying you can't have it, you can't have it. It wasn't an option when I was doing my second drawing. So the probability of red, red without replacement is 2/20. Wait, what happened? What's going on here? Why is it only 20? Well, the fundamental counting principle for the size of the sample space, it's my number of options for the first drawing, which is 5. Then I take one of those out and the probability is going to be reduced. So it's my sample space for my second drawing, because I pulled one of those balls out. There's only 4 remaining and my sample space is 20. What you're removing here, if we go back way in the beginning into our uncondensed, everybody's labeled, all the different balls have different numbers too. What's actually getting removed when you do with the without the replacement is the red 1, red 2, blue 1, blue 2, and blue 3, blue 3. Those 5 options are gone now. Everything else is still an option. That's what's happening when you do without replacement. You can't get the same ball twice if it's already been pulled out and it's not there anymore. Just a subtlety. Wow, we went through a lot in this video talking about balls and bags, tree diagrams, with replacement, without replacement. If you have any questions at all, please ask. I am available and I will get back to you as soon as I can. Uh, Thank you so much for watching. I hope to hear from you soon. Have a great rest of your day. Bye.